beautiful people, I'm going to jump in here and do a quick correction on the video to come. So in the video, I did misspoke or I did misspeak, and I wanted to make sure that when you are checking for extraneous solutions, you are checking the original given question, not the simplified version. Again, if you are checking for extraneous solutions, which you have to check every single time, make sure that you are plugging in your values into the original given question and not the condensed version. Original, think original, just plug it into the original. Whatever they give you, that's what you plug your values in. Now, what does it mean to have an extraneous solution? That means it doesn't work. For your extraneous solutions, if you have a log of a negative number, if inside the bubble you get a negative number, immediately that doesn't work and you have an extraneous solution. If you have a log base of b and you take the log of 0, that also immediately doesn't work. All right, beautiful people, I'm going to go ahead and stop here. Enjoy the rest of the video. Hello, beautiful people, and welcome. In today's video, we are discussing how to solve logarithmic equations. Now, there's going to be two parts of this, both in this video, but there's two parts of solving logarithmic equations, two forms. As always, if I make a mistake, I am human. Just let me know where the mistake occurs so that way I may learn from it. Before we jump into solving logarithmic equations, let's talk about our golden rule. Now, in my class, we call it the golden rule. It's not the official name of it. That's just what I like to call it. So it is b of x is equal to a if and only if log base b of a is equal to x. So let's talk about that. When I originally gave you this golden rule, I didn't really explain kind of where it comes from. It's just a golden rule that we're just supposed to get, take as fact. Now I want to go back a little bit and discuss what this is. The exponential form and the logarithmic form, these are actually inverses of each other. Now, we have previously discussed inverses. Inverses are the ones that you take your x and your y and you switch them. So let's go ahead and just prove this real quickly that these two forms are inverses of each other. So let's start with log base b of a is equal to x. The first thing that we are supposed to do when we do the logarithmic function is to switch the position of x and y. Before I do that, I'm going to rewrite this in terms of a logarithm. Actually, let's not do that. I was going to say, hey, let's use what we're trying to prove in order to prove it. To find the inverse of it, let's go ahead and switch the position of x and y. Well, what is x and y? So let's rewrite this here as log base b of x is equal to y. Sometimes you'll see it in this form. So let's switch the position of x and y. Log base b of y is equal to x. Then we can rewrite this in the form of a exponential function. So in this case, we have base, exponent, answer. Now this looks familiar. Base, exponent, answer. So as you can see here, and we're going to take that extra step to make sure that we have this in inverse notation, or in this case, f of x inverse here. So these are inverses. And why this is important that they're inverses is because with exponential properties, there are some things that can't happen. So let's talk about an example. So example of something that cannot happen. So if we have a base with any exponent, one thing that can never occur, and again, this is when base is greater than 1. I'm not talking about a base that's negative. We're talking about a base that is greater than 1. If we have a base with an exponent, it doesn't matter what that exponent is, you will not get a negative. even if your exponent is negative, like your exponent can be negative, your exponent can be whatever you want it to be. However, it will not make your answer negative if your base starts out being greater than 1. Another thing that cannot happen is no matter what your base is and no matter what your exponent is, you cannot get a 0. You can get a 1, you can have your exponent be 0, but you cannot have a 0. So that means your log, whatever base, again, we're talking about bases greater than 1, cannot happen. You can't take a log of 0, and you cannot take a log of a negative. This cannot happen. So knowing these two things, we're going to go ahead and go back to solving equations because we're going to talk about extraneous solutions. So extraneous solutions are solutions that we get when we solve things. However, in reality, they don't actually work. So let's talk about log equals log. We're going to give you some steps. Step number 1, always, is to condense each logarithm. Put everything together. You are then going to use the one-to-one rule. Now, what is the one-to-one rule? Let's do a little mini side thinking bubble. The one-to-one rule states that if log base b of m is equal to log base b of n, then you have those two things equal. Then m equals n. Just like when we had our one-to-one rule, I think it was the same base property that we called it. If our bases are the same, we set the exponents equal to each other. Same thing here. If the bases are the same, then your m and n are equal. Step number 3, solve and check for extraneous solutions. Now, one thing I do want to point out, so like note, I'll even change my color here. You're most likely going to use, not all the time, but note. You're going to use that golden property, that inverse, right? That notation. But one thing you need to note that log base b of a, this, whatever it is, that is in a bubble. You cannot split this up. You need to group together. And the only way to ungroup something like this is to use a property or the inverse definition, the golden rule. So it is grouped together. To break apart, you need to use property. And I'm going to call it, again, the golden rule. It's not the official name of it. So let's jump into an example. We'll start out with one easier example, and then we'll do one example that's a little bit more complicated. So let's say I have log base 5 of 5x plus 9. That's equal to log base 5 of 6x. One thing you need to note is that for your one-to-one property or one-to-one rule to work, your bases have to be the same. So in this case, I have a log base 5 and a log base 5. If your bases are not the same, you guys, everything goes out the door. Since I have log base 5 and log base 5, again, I'm going to use my one-to-one rule or one-to-one property. And that states that I can set these equal to each other and continue solving. Whenever you're solving for equations, you are solving for a value at the end. So then we're going to combine like terms. I'm going to subtract 5x both sides. So I have 9 is equal to x. Is that my answer? Maybe. We have to check for extraneous solution. Now, you may choose to show your work on this. I personally will probably, use a calculator. But basically what you're looking for, if you have a log equals something and a log equals something, you don't actually need to evaluate and make sure those sides equal each other. They do need to equal each other, but you don't actually have to show that work. So what I'm going to do is I'm going to take 9, I'm going to plug it in here. So I'm going to say log base 5 of 5 times 9 plus 9 is maybe equal to the log base 5 of 6x. And again, that x should be a 9, so times 9. Using my calculator, if you need to, you don't need to on this part. All I'm doing is 5 times 9 plus 9. So I get 54. 6 times 9 is also 54. So you already know that these sides are equal to each other because they're the same thing. So I don't actually need to know the value of log base 5 of 54. So therefore, yes, this answer checks, and you are good to go. All right, let's do an example that seems a little bit more complicated. It could potentially not be complicated at all. We'll find out. So example 2. Let's do log base 3 of 2p minus 5 is equal to 2 times your log base 3 of 6 minus your log base 3 of 4. First thing I'm noticing is I have all of my bases B3, so I am happy, meaning I can condense this. Step number 1 is always condense each logarithm. So you may potentially be confused, like, what do I even do? Step number 1, always condense. Once you start condensing, things will simplify and it will look much cleaner and you'll be able to decipher what to do. So log base 3 of 2p minus 5, that is the only thing on this side, so I'm just going to bring it down. However, on this side, I have two things happening. I have a number being multiplied by this log here, meaning this 2 is an exponent on that 6. I also have a minus in between those two logarithms. That means I have a quotient property. So let's undo that exponent by placing it back where it came from. I still have my minus. Evaluate as you go to simplify things further. So I have log base 3 of 2p minus 5. That's equal to log base 3 of 6 times 6 is 36. Put that in a bubble in case you get confused with the 3's. This is not a property. This is just log base 3 of 36. We still need to do the quotient. So log base 3 of 2p minus 5. That's equal to log base 3 of, numerator is always first, divided by 4. 36 divided by 4, use a calculator if you need to, that is 9. So log base 3 of 2p minus 5 equal to log base 3 of 9. Now here, after you've done all of this condensing, then you can start to see what's happening. You have a log base 3 and a log base 3 on both sides. Nothing else is there. That means that you can use the one-to-one property and say 2p minus 5 is equal to 9. Now, I am not canceling these out. It's not like I'm dividing by log base 3. Again, you cannot ungroup them. It's like you're super glued so close together right here. This is one thing. This is an exponent. This is an exponent. I can't undo that exponent. It's like having an exponent of 41 and then splitting up 4 and 1. You can't do that. You can use the one-to-one rule. Or in this case, one-to-one property. Same thing. All right, let's continue solving. I'm going to add 5 to both sides. Therefore, p is equal to 7. Maybe p is equal to 7. Maybe p is not equal to 7. What I'm going to do is I'm going to take this 7, plug it in here, and then solve. So once you solve for your x value, you have to plug into the original equation. So this is where the hiccup happens. You want to plug into the original equation. If you have a log of a negative number, or if you have a log of 0 inside each bubble, that means your value would be extraneous. As seen here, we did not get an extraneous value. However, the work does not match what we should be originally doing. Make sure that you're plugging into the original given equation, not the condensed version. All right, beautiful people, that wraps up this video. As always, I appreciate you and enjoy the rest of your day. Bye!